Operating a global ride-sharing network requires synchronizing millions of independent actors in real time. Every active driver and rider acts as a continuous data node, generating a chaotic flood of requests, location updates, and status changes across the physical world. Managing this chaos requires solving two completely different engineering problems simultaneously. The first is managing ephemeral state. A network of 1 million active drivers pings the server with GPS coordinates every few seconds. That creates an inbound workload of over 250,000 write operations per second. The second problem is managing transactional state. When a rider books a trip, money is authorized and contracts are formed. This requires absolute ACID compliance and strong data consistency to ensure a driver is assigned exactly one ride and a user is billed exactly the correct amount. These two workloads cannot share the same data store. If a system attempts to run 250,000 spatial location writes per second through a relational database, the table locks required for strong transactional consistency will choke the database, stalling the entire application. Compounding this constraint is a strict latency budget. When a user requests a ride, the system has roughly 10 seconds to process driver telemetry, aggregate regional demand, execute graph matching algorithms, and lock a database transaction before the rider closes the app. Missing this 10-second window directly degrades conversion rates and cascades into marketplace failure. To survive this constraint, the architecture decouples into three highly specialized pillars: location ingestion, dispatch optimization, and streaming pricing. To maintain an accurate map of supply, driver apps emit a location ping at a specific calculated interval, 4 seconds. Polling every 1 second drains the driver's phone battery and consumes excessive cellular bandwidth. Waiting 30 seconds leaves the data so stale that a driver traveling at 60 kilometers per hour could miss an assigned pickup intersection entirely. Sending these updates via standard HTTP requests introduces severe overhead due to repeated TCP handshakes. Instead, the driver app opens a persistent WebSocket connection to the backend, streaming a lightweight JSON payload of their coordinates with minimal latency. Standard SQL databases collapse under 250,000 queries per second. They are built for durability, not velocity. To ingest this fire hose, the system routes the data to Redis, an in-memory data store. Using specialized geospatial commands, specifically geoadd, Redis stores the driver's coordinates in memory, enabling sub-millisecond proximity lookups. Storing millions of moving coordinates in memory requires distributing the workload across a vast cluster of Redis servers. The challenge is ensuring that drivers in the same physical neighborhood are stored on the same logical server, so proximity queries don't have to scan the entire global cluster. This map shows raw coordinates snapping to a grid of S2 cell IDs. This ID acts as the database sharding key, routing the location right to a geographically isolated Redis shard. All drivers in a given neighborhood end up in the exact same memory partition. This introduces a new problem, the ghost driver. Mobile networks drop out, phones die, or apps crash without sending a logout signal. The driver physically disappears, but their last known location remains trapped in the spatial index as an available vehicle. Instead of writing complex disconnect logic, the system applies a strict 15-second time to live, or TTL, to every single location write. If a driver's app fails to ping the server for 15 seconds, the Redis key automatically expires. The driver vanishes from the available pool. Combining persistent WebSockets, S2 spatial sharding, and TTL auto-eviction creates a massive throughput ephemeral state that continuously cleans and heals itself. When a rider requests a trip, the dispatch service queries this fresh Redis index using a command like GeoRadius to pull a pool of candidate drivers near the pickup location. Ranking these candidates using straight-line distance ignores physical roads, one-way streets, and traffic. Calculating accurate drive times requires querying a routing engine like OSRM. However, running a complex routing algorithm for every driver in the radius takes too much time, violating the 10-second latency budget. To bridge this gap, the system heavily caches estimated times of arrival for common high-traffic corridors, like the route from an airport to downtown. This avoids redundant routing engine queries and keeps dispatch times well under 2 seconds. The most intuitive dispatch logic is greedy matching. If a rider requests a car, they're assigned immediately to the absolute closest driver. This simulation illustrates why that logic fails. If Rider A claims the optimal driver, Rider B, who requests a car a fraction of a second later, might be left with a driver 10 miles away. Greedy matching optimizes locally for the first request, but rapidly depletes local supply, causing severe inefficiencies across the grid. The system batches requests into 2-second windows, modeling the map as a bipartite graph, separating passenger demand from driver supply. Connections are weighted by estimated wait times. The Hungarian algorithm then identifies the exact pairing configuration that minimizes total wait times for the batch simultaneously. A specific rider may wait 30 seconds longer for their car, but the overall average wait time for the entire neighborhood drops dramatically. At this scale, matching algorithms are not simple if-then code blocks. They are complex operational research engines designed to balance mathematical equations of physical supply and demand in real time. Once the algorithm selects the optimal pairing, the dispatch service pushes the offer to the driver's phone via WebSocket. The driver has a 15-second window to accept. This creates a critical race condition. Network latency or batch dispatch retries mean two drivers could conceivably tap accept for the exact same trip at the exact same millisecond. To prevent this, the moment an acceptance hits the server, the trip service attempts to acquire a distributed lock on that specific trip ID within Redis. The first write wins the lock. The system then drops down to the highly durable trip service layer, powered by PostgreSQL, to commit the final transaction. This visual shows the precise optimistic concurrency logic executed against the database. The where clause acts as a final atomic safeguard. If another process has already updated the trip status to matched, the query affects exactly 0 rows. The transaction fails gracefully, the driver is told the ride is no longer available, and double booking is completely avoided. For the final millimeter of the 10-second lifecycle, the system intentionally abandons the blistering speed of eventual consistency in memory. It shifts to the absolute ACID reliability of relational databases to protect the integrity of the transaction. When demand outpaces supply, wait times increase exponentially until the grid breaks. To stabilize the marketplace, the system deploys a dynamic pricing engine to pull physical supply into critical zones and filter out price-sensitive requests. Uber's H3 spatial index uses hexagons, where distance from the center to all neighbors is uniform. The pricing engine computes real-time supply using an O1 set cardinality operation against Redis. Simultaneously, Apache Flink calculates demand by aggregating ride requests within a sliding 5-minute window. Dividing demand by supply yields a ratio, which maps to a pricing multiplier. But if a multiplier jumps abruptly from a 1.0x baseline to a 2.0x surge across a single neighborhood boundary, riders cross the street to get cheaper fares, and driver routing breaks down. To prevent this boundary effect, the system applies spatial smoothing mathematics, utilizing Kalman filters or exponential moving averages to gradually blend surge multipliers across neighboring H3 cells. Once a user sees a surge quote, the system writes a 60-second surge lock key to Redis. This ensures the quoted price does not update underneath the user while they navigate the checkout flow. Dynamic pricing is an automated, stream-processed control loop. It relies on real-time spatial indexes to continually adjust the physical distribution of cars across a city. Looking at the complete data flow, we see client WebSockets feeding into API gateways, branching out to the location, dispatch, and trip services. The scale of this network requires rigorously separating microservices based entirely on their required data consistency. Eventual consistency rules the ephemeral layers. High-throughput tools like Redis and Flink handle telemetry and pricing. Strong consistency rules the transactional layer, relying on PostgreSQL to securely lock bookings and payments. The architecture assumes failure, dropping stale GPS pings, bypassing slow routing with cached ETAs, and gracefully failing concurrent database locks are deliberate design choices that keep the system moving. Delivering a rideshare match inside a 10-second window requires the architectural maturity to accept partial availability in the telemetry layer in order to guarantee absolute reliability in execution.